Okay, I think we can get started. First of all, good morning, everyone. Well, at least for me, it's the morning. So, good morning, everyone. For those who still don't know me, I think you've seen me like many times in almost every single talk. My name is Melissa. I am the scientific program coordinator of the International Conference of Physics Students, Puebla 2022. And again, it's a great pleasure for me to introduce our next speaker, our first speaker today, who's going to talk us about searching for neutrinoless double beta decay at SNOLAB. So Dr. Caden completed a postdoctoral fellowship at Laurentian University, working on calibration, source, shielding, and hardware development for Snow Plus. As a research scientist at SNOLAB, she works on the Snow Plus, Halo, and Nexo experiments. Dr. Caden was the Snow Plus detector manager until 2019, leading the everyday working of the experiment through its initial commissioning and water physics phase. She currently serves on many internal committees for both Snow Plus and Nexo, as well as on the Science Council for the Institute of Particle Physics in Canada. One of Dr. Caden's longtime passions is science communication, and she had created many art projects used to explain complex physics concepts. She is the teaching director for the Girls Initiative, a summer camp program she co-founded to encourage young girls to study science. Dr. Caden was recognized as one of Sudbury, Ontario, Canada's young community leaders with a 40 under 40 award in 2019, and as one of Drexel University's 40 under 40 outstanding alumni in 2020. Without further ado, please join me in welcoming Dr. Erika Caden.
Thank you very much for that lovely introduction. The last time I was in Mexico was speaking at a summer school in Sonora. So I would have loved to have been back to see you all in Puebla. But I will be talking about searching for neutrinoless double beta decay at SNOLAB. So we'll have a brief overview of neutrino physics, then talk about double beta decay, and then about SNOLAB and the experiments that are searching for it and why it's important. There we go. To start off, as is the custom in Canada, I am not from Canada, and most of the people who are living and working in Canada are not from here. We are immigrants and the sons and daughters of colonizers. So Sudbury is located on the traditional territory of the Robinson-Huron Treaty of 1850. And this land is shared by the Indigenous people of the surrounding Atikamekw and Anishinaabe First Nation as part of the larger Anishinaabe First Nation. So we acknowledge those who came before us and honor those who take care of this land and the waters. So continuing on, what is the neutrino? I was not sure exactly the background of everyone who would be here, so I thought I'd start a little broadly. We know apples. We know the apple fell from a tree and hit Newton on the head story. We also just know apples are generally delicious and make a great pies and salads. And apples are made up of atoms. And so these atoms have images from the particle zoo, little plushies. So atoms make up everything. And so we have protons and neutrons in our nucleus and electrons around the outside. But this really leads to a whole wealth of the standard model of particle physics. So we have the bosons and the fermions. We have then fermions are split up into quarks and leptons. So the quarks make up the nucleons and other exotic particles. And here down at the bottom of the leptons, we have the neutrinos. So what we do know so far about neutrinos. I'm not going to get too much into all of neutrino history. That is for another talk. But we know that they were first postulated in 1930, so less than 100 years ago, and they were not discovered until 1956. So 26 years between when they came up, the idea was formed that saved a bunch of our closely held theories of conservation, and then until they were finally experimentally verified. So they are fermions, which means they're spin 1/2. They are leptons, which means they have no color charge like the quarks do, and they are neutral, so they have no electric charge. So all of these quantum numbers together really lead to some interesting possibilities. They only interact via the weak force, not the strong force or the electromagnetic force. We have 3 flavors of neutrinos with kind of associated with the 3 generations of particles. Each neutrino has its own associated charged lepton, so the electron, muon, and tau, they each have their own neutrino. They can oscillate from one flavor to another. So a neutrino that is born as an electron type neutrino won't stay an electron type neutrino forever, depending on how far it goes until it interacts. It will change between muon and tau. And this happens to all neutrinos, no matter where they are generated. This also happens in the quarks, but not to a huge degree. The alignment of the mass eigenstates, the flavor eigenstates of neutrinos are just completely spread out. So this again leads to some very interesting questions. We also know that they are the most abundant mass of particles in the universe. We only have more photons than we do neutrinos. So there are 340 per cubic centimeter of neutrinos everywhere. So this is what we know after studying them theoretically since 1930, and then actually being able to experiment on them since 1956. This is all we know. What we don't know about neutrinos is even more. Are there only 3 neutrino flavors? Are there more? Are there only 3 neutrino mass states? Could there be a sterile state that doesn't interact with the flavors? Which neutrino is the heaviest? As we normally think of the generations of particles, we have up and down are light, strange, and charm are heavier, and top and bottom are the heaviest. And the tau is the heaviest lepton. But is the tau neutrino the heaviest neutrino? The masses aren't aligned. It's not clear. Is the 3rd neutrino the heaviest neutrino? That is also still unknown. We don't know what the mass of the lightest neutrino even is. We know it's not 0, but we don't know how much more above 0 it is. Why are neutrinos so much lighter than any other particle? There's orders of magnitude between the masses of the neutrinos, the maximum masses so far that we know they're less than something, and then the mass of the electron. What is the quantum nature of the neutrino? So that's going to be the questions I get into. And why are we living in a matter-dominated universe? Everything we see is matter. We know that is only 5% of what is in the universe. Could neutrinos help answer that question of why? So now that's everything we know about neutrinos so far, and everything we need to get into the rest of this talk. So double beta decay was first theorized by Geppert-Meyer in 1935. So again, neutrinos had just been postulated as the solution to the beta decay problem. So we were seeing beta decays and only seeing the electron, but the electron didn't have a certain energy. And we realized in the reaction, the electron was sharing its energy with the neutrino, and the neutrino was taking away different amounts of energy. So they were sharing the sum total energy of the decay. So we could have twice in one nucleus, depending on its atomic numbers, even nuclei, where a single beta decay is energetically forbidden. You could have double beta decay, so it moves by 2, and you have twice at the same time 2 neutrons decaying to 2 protons, 2 electrons, and 2 antineutrinos. So this is completely allowed in the standard model, and we've seen it in 12 isotopes so far. So cool. Okay, awesome. We have another kind of decay. In 1937, Ettore Majorana suggested that maybe the neutrino, because it's spin 1/2, because it doesn't interact with color, because not that we knew what color was at the time, or I mean, we barely knew what electric charge was at the time, but we knew it didn't have any of those if it followed all of the other theories that we thought it did. Maybe the neutrino could be its own antiparticle. So maybe the neutrino and the antineutrino could be the same. So this is really interesting if you put that together with Geppert-Meyer's theory, which is what Furry did in 1939. Again, 17 years before we had any evidence of the neutrinos, we had the idea of double beta decay with no neutrinos. So a neutrino-less version where the neutrino and antineutrino kind of self-annihilate inside. There's some Majorana process inside the nucleus, and you only eject out the electrons, which is what they had been expecting for the original beta decay. You only expected to see electrons. So this reaction has not yet been observed that Furry postulated, but it implies a non-conservation of lepton number. And we love when all our conservation laws get broken. So we have a reaction that produces 2 leptons and no anti-leptons. And this reaction implies that neutrinos are Majorana particles. There is some Majorana process that breaks lepton number conservation going on inside here. So this is why we think this would be so cool to see. So how would we see this? So with beta decay, there was a huge spectrum of the beta energies, and they were looking for just a single beta energy. So we are looking for the same thing with double beta decay. We're looking for a peak at the Q value of the decay that is then kind of smeared. It won't be an exact peak. You'll have detector energy resolution to smear this a little bit. And of course, it's not so beautifully separated like this. It looks more like a small hump at the very end of the decay of the Q value range, just kind of next to this 2 neutrino shoulder. So to be able to see this, you need a lot of isotope. We know this is very, very rare. 2 neutrino rates happen on order of 10 to the 20 years is their half-life. So to have enough atoms to possibly see this happen, you need a lot of mass. You need really good energy resolution to be able to separate this peak from this shoulder. So to really understand your detector's response. And you need low backgrounds. If this represents something that has a half-life of 10 to the 20 years, this tiny shoulder here, we're looking for things now that are on the order of 10 to the 27 or 10 to the 28 years. So much older than the lifetime of the universe. And to look for this tiny hump, you need really low backgrounds. You need to make sure that the rest of your detector is very, very clean to be able to pick up the signal off of almost no background. So these are not easy experiments to do. In addition to that, how do we even look for it? What are our candidate isotopes? We said even ones where single beta decay is forbidden. So that leads generally to these handful. So these are the ones that are easy to see that we have observed so far at the 2 neutrino half-life, and that have an energy above natural radioactivity. There are others that have decay energies below, but then that makes it very much harder to see. So we can choose our isotope based on a few things. The 2 neutrino half-life. So you want a long 2 neutrino half-life so that shoulder lowers, so it's easier to see. You want you can pick it based on Q value. So what is the energy that you're looking for? Again, getting outside of that radioactivity, we are only looking at ones that are over 2 MeV. Certainly, even some of these are difficult depending on your detector technology. You can look at natural abundance. How much of the isotope of every handful of atoms that you have, how many of those are the isotope you're looking for? Or do you need to enrich? Something like calcium-48 has a great Q value, way above anything else, but it's like 0.1% natural abundance. So you need to get a whole lot of calcium before you can get any of this isotope. And you also want to think about your detector compatibility. What is the technology you're going to use to look for this reaction? And can you make your isotope work with your technology. But really, when it comes to all of this, what does it matter if we're looking for some tiny peak in some energy range? What does this actually give us? So observing neutrinos double beta decay will revolutionize our fundamental understanding of neutrinos. So I talked about the many questions we have still in neutrino physics. And what we're measuring is this rate. We're counting. This is just a counting experiment. And we can relate this half-life into a rate by a phase space factor, by a nuclear matrix element that itself is not very well known. None of the theories agree with current experiments, and none of the theories agree with each other. This always gives you a range of values, but it eventually relates to this effective neutrino mass. So we talked about how we don't know what the neutrino mass is. We don't know which neutrino is the heaviest, how many questions there are still about neutrino masses. But measuring or putting limits on the rate of neutrinoless double beta decay can push down what this effective neutrino mass could be. So we have the inverted hierarchy and the normal hierarchy. So if the third neutrino is heavier than neutrino 1 and 2, or if it's lighter than neutrino 1 and 2, lighter would be this inverted hierarchy. And we can start to possibly rule out that if we don't see neutrinoless double beta decay with a rate that gives an effective neutrino mass here, then there's no way that the third neutrino could be heavier than the first two. So we can start to, by not seeing any neutrinos in our end product, we can start to tell more about neutrinos than other detector concepts. So this is incredibly interesting. We would learn about lepton number conservation and how it's violated. This would prove that there's a Majorana nature to neutrinos, which makes them different than all the other particles. Every other particle we have is Dirac, but just because neutrinos could be Majorana, we should look for it. And neutrinos are weird in every other way. Why shouldn't they be weird in this extra way as well? This could explain the matter-antimatter asymmetry in the universe, because now we have a reaction that creates 2 leptons and no anti-leptons. We have now demonstrated an asymmetry for matter. And again, it can constrain the neutrino absolute mass scale, because we're pushing down and we're putting more stringent limits on the mass. So there's a lot that neutrinoless double beta decay can give us if we observe this. But again, I kind of talked about how difficult it is to build these detectors and what you need to actually see the signal. So that brings us to SNOLAB, which is where I work and which is the best place on the planet to do the science. So if we took a road trip, if I were to come visit you, there are a number of ways that I could go. But we are up here in Northern Ontario. It's about a 4-hour drive from Toronto, maybe 6 hours from Ottawa. It is lovely right now this time of year. We are sunny and warm. There's great hiking in Sudbury. If you were to fly in to SNOLAB, if you were to helicopter in, this is what you would see. We are located on an active mine site. So Sudbury is one of the nickel capitals of the world. If you have a stainless steel sink in your home, you probably have a little bit of Sudbury in your house. So they mine nickel and copper and some other heavy metals here. And this mine has been operating since 1900. So this is a well-established mine. And here is our surface building where we have offices and some machine shops and some clean lab space. But what's interesting about Sudbury about SNOLAB is the underground campus. So we go 2 kilometers down a mine shaft. So 6,800 feet, or about 7 times the Torres Obispado tower, that is the tallest tower in Mexico and in Latin America. So 7 times taller than that, we go down in an elevator. And then we walk 1.5 kilometers to get to the lab. So we do that because we want to, the underground environment is the best environment to do this kind of science. So here's a video made by Zach Kenny at the McDonald Institute. that shows the cosmic rays interacting in the atmosphere and producing these showers of particles that just rain down on surface. And here's our Snow Lab surface building. But as you go deeper underground, the 2 kilometers of Earth starts to shield out these particles. So whenever you have your experiments underground looking for some reaction like that, you have less of this other noise from surface that could interact in your detector. So you use the Earth as shielding, but that's not the only shielding we need, but it helps dramatically. You can't do these experiments on surface. So here is a plot of the total muon flux, and that's mainly what we're shielding out is muons of many energy ranges versus effective vertical depth. So we have some labs around the world that are in underneath mountains, and we have some labs that are inside mines. So here are the labs that have vertical access in mines, and even some of the labs that are underneath mountains. These are mines under mountains, but you go in sideways instead of going down. And Snow Lab has the lowest total muon flux because of any lab anywhere. And even if you're underneath the mountain, you have this great vertical shielding, but muons can come in from the sides too, and they don't provide as effective total azimuthal shielding as going into the Earth when you have even more shielding on the sides. So Snow Lab's lowest total muon flux of any lab. And the 2 kilometers of rock reduces this cosmic radiation by a factor of 50 million. But it doesn't stop the neutrinos, and it also doesn't stop dark matter. So Snow Lab is home to 2 neutrino experiments, 6 running dark matter experiments, and 2 biological experiments that take advantage of our entire clean room space and the infrastructure that we have created. So we're 5,000 square meters of class 2000 clean room. So class 2000 means that there are fewer than 2,000 particles that are more than half a micron in diameter per cubic foot. So that's a weird combination of units, but it means we're essentially as clean as an operating room. But that's the size of a shopping mall inside an active mine. So it takes a lot of work to maintain the lab to this level just to let the science happen. So I would love to take everyone on a tour of Snow Lab. It's one of my favorite things to do is show everyone how cool our facility is. But this will have to suffice. So we would walk 1.5 kilometers, again, through these mine drifts, through these tunnels that are blasted out with rock, and screening put on to stop any small pieces of rock from falling on our heads. We would then get into the Snow Lab, or we call it the double track area. Everything that comes into the lab comes in the way we do. There's no back entrance to move these large pieces for our experiments. Everything comes in on these rail cars, we call them, or we carry it in. So here's also where we would wash off our boots, or our first step in cleanliness. Then we wash ourselves off. Every time you come into Snow Lab, you have a shower. You wash your entire body to get all of the mine dust off. You wash your hair. Every single day you go underground, you wash your hair. And then you put on clean room coveralls so that you are, you don't have your dirty mine clothes. So that's one of the first steps, is making sure everything that comes into the lab is clean. We have lots of infrastructure. We have very well lit hallways, and we have air handling units to filter the air that comes in and remove all of the mine dust that we've just washed off of us. We don't let that come in the air systems. And we have large electrical infrastructure too to support the experiments. We have halls that have storage for future projects. So this is some cable trays and some ducting, and we have a support structure for then building the next pieces of experiments. Everything has to be reused, so everything is come down and cleaned initially. Every single piece of every single item inside Snow Lab is cleaned by hand, scrubbed inside and outside of every piece of tube, every thread on every bolt. Everything is cleaned before it can be used in our experiments. Our machine shop is the cleanest machine shop you will ever see. It has It's necessary to adjust some of the parts for our experiments. Maybe your hole isn't in quite the right spot. Once it's actually put together, you need to slot it out a bit so you can fit the bolt in. This is the cleanest machine shop you will ever see. And we save so much time on our schedules by being able to make these modifications in-house underground. So we have some experiments that are small. So here are a series of smaller dark matter experiments that kind of fit inside a hallway. We can use a lot of this space for research and development as these experiments grow. But we also have one last large cavern that's called the cryo pit that is designed for a cryogenic experiment looking for neutrinoless double beta decay. So this will be the home, hopefully, of one of the experiments I'll talk to you about. So we saw that kind of map of the lab before, but this is really how full it is with different experiments, different lab facilities, future projects that will be coming online. The neutrino experiments are outlined in orange. The dark matter experiments are outlined in black. Some of the process plants are in silver. The biological experiments are outlined in green. There is so much going on at the lab. We employ about 150 people, and that's more than double when I started working at Snow Lab 9 years ago. It's huge how it's grown. So with all of the infrastructure that the lab has put into supporting experiments, as well as its deep location, it is the best place in the world to do double beta decay. So I'm going to talk about two experiments that are looking for this. One is Snow Plus. So Snow Plus is a multi-purpose, the other one is Nexo, and I'll finish off with Nexo. So Snow Plus is a multi-purpose experiment that had been filled with 900 tons of water and is now filled with 780 tons of liquid scintillator. It is again deep underground, 2 kilometers of rock overburden. I say it is filled, that is our acrylic vessel, which is 12 meters in diameter, but just 5 centimeters thick of acrylic. It is surrounded by 9,300 photomultiplier tubes that see the signal, the light that is generated from reactions inside the central acrylic vessel volume. All of this is inherited from the SNOW experiment for which Art McDonald won the Nobel Prize in 2015. They kind of showed solar neutrino oscillation. It was filled with heavy water and had to be held up, this sphere, because heavy water is heavier than regular water. So there were these hold up ropes. So now that it's filled with scintillator, is mineral oil based, it is lighter than water, so we have to hold it down. So there's this rope net that anchors it down into the ground. And it's surrounded by 1,700 tons of water shielding inside between the PMTs and the vessel. And there's another 3,700 tons of water shielding inside the cavern. So Snow Plus has a broad physics program. There's a lot of questions that can be answered with one detector, which makes it a really interesting experiment to work on, that there's so many analysis topics. So we are able to see solar neutrinos, and we have multiple papers on those. We are sensitive to a supernova. We could see different modes of invisible nucleon decay. Moving on, we can to antineutrinos. We can see neutrinos generated in the Earth and from nuclear reactors. But its main purpose is a double beta decay experiment. So our results in our water phase, so we were first filled with this 900 tons of water, are all of these papers, understanding our backgrounds, the solar, the nucleon decay. We expect to be able to see neutrinoless, inverse beta decay, so to see reactor neutrinos in plain water, in undoped water, which had not been seen before, because we have a really high neutron detection efficiency. And we actually just improved our invisible nucleon decay results. So this is looking for a neutron or a proton to decay in a way, well, we've never seen a proton decay. Hopefully we don't see a proton decay, but there's no reason it shouldn't decay. And many a lot of the field of neutrino physics came about because they were building giant water detectors looking for proton decay. So we put improved limits on that. So right now, we filled with water, we did some physics, we then put our scintillator in and drained the water out of the bottom and filled our scintillator with more chemistry to get light out in the right wavelength. So that is this PPO at 2 grams per liter. And we are now watching the radon levels decay away so we can continue to do physics. We have all of our backgrounds from the uranium and thorium chains that would produce light in our region of interest are decaying away at acceptable levels. We can then use some of the backgrounds, the bismuth and polonium, to measure our light yield, so 300 photons per MeV during our partial fill when we were halfway filled. Even during the pandemic, there was still constant access underground to SNOLAB, and we were able to continue to fill the detector and then finish the PPO loading. So SNOLAB was an amazing location to be able to keep working during when everything was shut down. So we've deployed our calibration sources external to the detector, and we're still working on finalizing the hardware to deploy calibration sources now into the loaded scintillator. And we're doing physics. We have improved boron 8. This is from the partial fill, and we're working on this analysis now that we have a full scintillator detector. And we're still searching for antineutrinos now with our scintillator, and we will continue to be live for if a supernova occurs. So with the tellurium phase, we will load 0.5% by weight of natural tellurium. So that's 3.9 tons total with 34% natural abundance. We don't need to enrich our tellurium. 1 out of every 3 atoms is the isotope we're looking for. So we can, so this gives us 1.3 tons of the isotope of tellurium-130. And this can be scalable to higher loading without changing much of the detector. So that we will have, expect to have very low background counts, 5 by 10 to the -7 counts per year per kilogram per KeV. And all of the backgrounds have been measured before the tellurium is added. So having this phased approach lets us measure our external backgrounds and then our internal backgrounds. And the only thing left to measure before we put in the tellurium, or after we put in the tellurium, will be the 2 neutrino rate. So here are the plants to purify the telluric acid and mix it into a butane diol complex that will load it into the scintillator. Organic hydrocarbons don't enjoy having heavy metals loaded into them. You have to really create new chemistry to get these molecules to bond and to have it not kind of settle out. So that's what this butane diol complex does. So in our region of interest here, this is assuming a 100 millielectron volt effective neutrino mass. This is what a signal would look like in SNO+. We have our background of the boron 8 solar neutrino electron scattering. That is very flat, and we've measured that rate, so it will be easy to subtract. We have already measured the externals, the backgrounds from the ropes and the PMTs themselves and the external water, and that's very small. We are measuring the backgrounds of the scintillator itself, the uranium and thorium chains. So this will be measured, and all that will be left to understand in this region of interest is the 2 neutrino rate. So this phased approach has been really beneficial for SNO+. And after 5 years of running at this initial 0.5% loading, this is the rate that we would measure, that we would be sensitive to, is a half-life of more than 2.1 by 10 to the 26 years. So this is just with 0.5% loading. We can increase our loading as well. So this would push us into measuring into the inverted hierarchy if we see neutrino double beta decay. But of course, then if we have increased our loading, then we can push through into just the normal hierarchy and rule out the inverted hierarchy. So now moving on to NEXO, which is a larger next generation experiment. So different isotope, different technology. NEXO has a time projection chamber at its heart filled with 500 kilograms of enriched xenon 136. So that's 90% enriched in the isotope we're looking for. So 5 tons in here compared to the 1.3 tons in SNO+. There's an active outer veto that actively vetoes muons, as well as layers of passive shielding. The xenon itself has very low intrinsic backgrounds, and this monolithic design, it looks tiny here, but 5 tons is huge. This is like 1.3 meters is the diameter of the TPC. It means that we can really self-shield from our external backgrounds, that the inner volume will be unaffected by backgrounds of the copper TPC itself. It will all be housed within a cryopit, or I'm sorry, within a cryostat. And this is imagined in the SNOLAB cryopit. So here is another view of that from the engineering layout side, where we have all of the different pieces, the grains, the xenon, the calibration system, xenon recovery tanks, water circulation for the tank, cryostats, refrigerant from the cryostat, liquid nitrogen to keep everything else clean. Everything that we will need has been figured out how it will be laid out in SNOLAB. So time projection chamber, different than the scintillator detector where you have just extra light coming up. We have a single drift volume. So you have filled with xenon. And if you have an atom of xenon that double beta decays, you would produce these 2 electrons. Again, these are the particles of electrons. There's an electric field, so they drift to charge collection tiles here on the cathode. But xenon also scintillates, so you get light coming off that hits these light collection tiles on the sides. So charge tiles here read out the charges. So this gives you an XY inside your detector of where the reaction happened. And then SIPMs collect light. So this gives you a T, so a time for when compared to where the XY hit, where also gives you extra energy information. But you can combine the charge and the scintillation signals to give you 3D reconstruction inside your detector of where the events happened. Also, this combination of light and charge gives you really, really good energy resolution. So the scintillation light collected from the SIPMs is plotted on the y-axis, and the charge collection, so the energy from the charge and the energy from the scintillation light, the charge tiles on the anode are on the x-axis. And for, say, a thallium-208 source, you would have a broad distribution in ionization energy, and a broad distribution in scintillation energy, but you can rotate your energy axis to give a very narrow distribution. So you can kind of convert between, you can combine the scintillation and ionization energies to have your rotated, very, very fine energy distribution. So the original EXO experiment, EXO 200, had 1.2% energy resolution. NEXO expects to have 0.8% energy resolution. So this means that you can very well tell your 0 neutrino energy peak from the edge of your 2 neutrino tail. So this is very important for these experiments. So this TPC is housed within a cryostat, a two-part cryostat. The inner vessel is filled with refrigerant, and the outer vessel is filled with vacuum. And this is all suspended within this outer veto that is an active veto filled with PMTs to veto muons. So muons would produce neutrons that would produce xenon-137 that would, and when that decays, it looks very similar to the 2 neutrino decay. It's in the same energy range. So this is very necessary to confirm a signal that our 2 neutrino or a 0 neutrino signal is not accidentally a xenon-137. If we see something in the muon veto, we cut that event, and so we have a very clean signal. Also, if we have a supernova within a few kiloparsecs, we would be able to see the neutrinos inside this outer detector, and that's the part of the experiment that I work on. So, because we're still looking for because no one has seen neutrinoless double beta decay yet, it is still a broad scientific program globally. So even if we see it in one experiment, we still have a range of those nuclear matrix elements so that we are not able to completely pin down the effective neutrino mass. We still have a range. To really understand the nuclear process, we need to have multiple experiments with multiple isotopes looking for this. So SNOW+ and NEXO aren't competitors, really. We need information from both of them. And we can say the same about the germanium experiments and other cryogenic experiments that are using different detector technologies and different isotopes. But I still have to plug for NEXO that I think it's the best because of its unique monolithic size, that you don't have many crystals that you're adding up all of the different surface area components. You have one large detector. So this 2.5 MeV gamma from some background cannot make it very far into the center of your detector. Xenon enrichment is cost effective. So for all of the xenon that we don't want, we can sell back to the dark matter community or other industries that use xenon. We have a multi-parameter analysis. So we're not just looking at the energy of the decay. We have many handles on what this signal will look like. And we can always put inside unenriched xenon or depleted xenon to see if the signal goes away or if there's some background that we have not accounted for. So our sensitivity is based not on, so this is a bit of a busy plot. We have our total inside fiducial volume, and we can keep cutting out the outer parts of the detector to look in to just the inner 1 ton of signal. We can look at single site events versus multi-site events. So I said how we had that 3D position reconstruction. We expect that a double beta decay will look like a single site event, and a multi-site event will be more like a background. So we can use that position reconstruction to separate our backgrounds from our single site events. And we also have that really great energy resolution. So we can combine where in the detector it happened, if it looks like a single site or a multi-site event, and what is the energy range in all of these different slices of the detector to separate, to really understand our backgrounds versus our signal. So for an imagined signal is in red as we look at only single site, not multi-site. We don't expect it to look like multi-site. And we go deeper inside the detector, we can really pick out this peak of what it will look like, because we will understand our backgrounds so well using all of the other information. So we can't reduce just a single background count per ton per year because we use all of that information as well. So then we have a projected sensitivity of 1.3 by 10 to the 5. 1.35 by 10 to the 28 years after a 10-year half-life or 10-year lifetime. So running for 10 years, this is what we would be sensitive to. And we could say that we have 3 sigma confidence of discovery at 0.74 by 10 to the 28 years. And so this leads to an effective neutrino mass that we would measure of 4.7 to 20.3 millielectron volts. So that gives us sensitivity down here after 10 years of running. So we are pushing through this normal ordering, this normal hierarchy, and really exploring our neutrino, pushing through the inverted into the normal. So we can say, is the ordering of neutrinos normal? Is it that the third one is lighter than the first 2? So this is our sensitivity paper that was actually published in the Journal of Physics G earlier this year. So in summary, NEXO and SNOW+ collaborations are who I work with. Neutrinos are fascinating. I could talk just about neutrino history for an hour. I could talk about Snow Lab for an hour. I could talk about other experiments. There's so much interesting stuff about neutrinos. Neutrinoless double beta decay is a pathway to new physics, no matter what we see. If we keep pushing the limit down, then we know neutrinos aren't inverted ordering. If we see something, then we know that there is some Majorana process, and we can start to try to untangle that, especially if we see something in multiple isotopes. If multiple experiments have a positive result, then we can really start to drill down on what are the details of these reactions. So Snow Plus and Nexo are both great tools to study neutrinos double beta decay and neutrino physics in general. And then really Snow Lab is the premier location for underground physics. So I am open to any questions, and you can learn more about Snow Lab on all of the social medias, and Nexo itself has a Twitter. So thank you very much.
Yeah, thank you, Dr. Caden, for accepting our invitation. I feel like everything you just talk about is like amazing, not only because I also did my master's in it, my master's thesis in it, but like I find it like very, very interesting. So now we are moving to the questions. So if people have some questions, you can just drop them in the chat, or if you want to open your mic, you are free to do that. So let's see if anyone has a question. Okay, in the meanwhile, I think I do have a question. So we were talking about before that one of the purpose of all these labs being like down the earth, like 2 kilometers or something down the earth, is like to have the earth to act like a shield from the exterior, right? But what about like emissions coming from the center of the earth? Like how do we treat them?
Yeah, so that's a great question. So one of the let me get back to say oh, there we go. There, so yes, so we shield cosmic radiation by going deep underground. But then there's also, we still have the materials our detectors are made out of. Actually, so maybe then this one is better. So we have then this whole area of the lab right here is called the car wash. So this is where we clean all of the other detector materials, so that they're not coated in exterior dust. But we also have our low background counting lab, so that we know that the materials that we've chosen don't have any intrinsic radioactivity. So we can count with gamma counters, with also electrostatic counters, what is inside our material. If you pick a plastic or an acrylic or an O-ring or a glove material for your glove box, or even an epoxy to put some things together, you can have that counted to make sure that those materials don't have some high source of radioactivity that would, while you're kind of putting something together inside your detector, you're now adding an extra background. So this is a service that Snow Lab provides to the community because our whole lab is so deep. Our detectors are more sensitive than others on surface. So this is how we make sure that our detectors themselves are made of clean materials. And then we have layers of shielding. So I talked about the water tank around next. So Snow Plus is sitting in a cavern that's flooded with water. The water shields from other neutrons that are produced in the rock. Other experiments, a lot of the dark matter experiments have ancient lead that stops gammas. Also borinated polyethylene that stops neutrons, ultra clean copper that does not have very many backgrounds, it can be electroformed underground. So we can take very good stock copper, create a mandrel, a shape. We can then electro deposit copper onto that shape, remove the inside shape. So your entire detector is created underground and you have only copper, none of the other backgrounds, because they are not electrolysis. the electrolysis process does not permit them to form onto the mandrel. So there's many different ways that we can design our experiments to prevent backgrounds from coming in.
Oh, that's actually really cool.
The
Okay.
electroformed copper is really, really neat.
Yeah. Does anyone else have a question? Because I have another question, but I would like people to ask. So there's a question in the chat. Let me just read it. So Sophie says, thank you so much for that presentation. My question, how can we extract results using these experiments, knowing that previous experiments has shown that double beta decay gives zero neutrino?
Right. So that is a good question. How do we possibly get anything out of it? So I think I'm going to use this slide to show. So why have we seen nothing so far in other experiments? Is it that we didn't have a nice enough isotope, or is it that we didn't have a clean enough detector, or that we didn't have good enough energy resolution? All of these things, these three things are really important to try to extract some signal. So if we don't have enough isotope, or if we don't have low enough backgrounds, this small hump here will be hidden underneath this. So this is a stacked histogram. I mean, obviously this is simulation. And when we're looking at data, all we have is our points. So we don't know yet why we haven't seen a result, but we can then say, using our detector simulation, what we would see. So if we don't see any, if we see no events, we would know that this half-life of this decay is longer than than what we could measure. So if it's longer than this, then we know we need either more isotope or a cleaner detector, or maybe better energy resolution. Maybe this is hiding in here and we don't have this fine energy resolution. I think 3% is what Snow Plus has, and that less than 1% is what Nexo thinks we can achieve based on our R&D and our previous experience. So all we can do is then take these limits and improve all of our detector components. We assay every single part of the detector. We know the background contributions from the resistors that do our field gauge, from the cables that take the signals out. So one of the interesting things about Nexo is that all of the those tiles, the charge tiles and the SIPMs, are sitting in the liquid xenon. These are cold electronics. So they need to be able to perform in this cold environment. And all of their components have to be extra clean too, so they don't provide contamination into the xenon. So we can keep coming up with new ideas of how to do that while trying to extend this half-life. We know it will be greater than some value. I hope that answers the question.
Yeah, I think there's another question in the chat. So Cesar Martinez says, thanks for such fascinating talk about antineutrinos. Are they detected the same way, or how the antineutrinos are detected?
So this is a good question. So in Snow Plus, the detection method for antineutrinos is called inverse beta decay. So you have an antineutrino hit a proton and produce a neutron and a positron. So yes, antineutrino hits a proton, neutron, and positron. Yes, all of that works out charge-wise. The positron then hits immediately annihilates with an electron and produces two gamma rays, and we see them in the scintillator. The neutron eventually captures on a hydrogen atom and produces a 2.2 MeV tag. So we see this two-part coincidence. That's how we know we have an antineutrino. But with the solar neutrinos, we see those through electron scattering. They bump off against an electron, and we see a Cherenkov cone. So there are different detection ways that we would see the different particles in Snow Plus. So Nexo is different than Snow Plus in that it's a detector that is more singularly focused just on double beta decay. So we're actually not seeing neutrinos in Nexo. We're just seeing the electrons that come from the double beta decay. And so those electrons drift through the charge field when the two neutrino reaction, or when the double beta decay reaction happens, the electrons drift. And so we see the scintillation light from the ions, and then the charge collection. So there are different detection methods in the two experiments.
Okay, cool. So I think we just ran out of time for more questions, but if you have more questions, you can just ask them in the questions channel of Discord, and we can just send Dr. Caden an email, and maybe she will answer.
Absolutely.
Okay, so thank you again for your talk. It was like amazing. And I would like to make just a couple of announcements. First, we are going to take a break now. The next hour for you guys is free. And then we are going to return in an hour for our science and cooking class. So we are going to have a chef from Chile. He's an expert in science and cooking. So he's going to give a class about cooking, but using but from a point of view of thermodynamics and all that stuff, and physical chemistry. So I really encourage you to join us. So the science and cooking class will be held in Zoom. So you can check the link in the calendar. And I would like to just add that Haynes Wood, who's the chef for the next class, he has a very successful account on Instagram. He has more than 130,000 followers. So make sure you attend to the talk. Okay, so I think we are good now. Thank you again, Dr. Caden, and I'll see you guys in an hour.